right? And here we saw that, we had subsets, and we were interested in those subsets which were subspaces, in the sense that which were closed under addition, where we could do some kind of arithmetic. Okay. And even when we were starting with subsets which were not subspaces, we took their linear combination and we made them a place where you can do arithmetic, and which is geometrically interesting in some sense. Okay. So just it really depends on what we are trying to do. Example, when you're doing analysis and you take a set, or when you take q, right, you make sure that it has least upper bounds, and so you make it analytically complete, and there you get r, right? So that's because you want to solve problems, like you want to use, or you want to use your subsets to parameterize time, or you want to use your subsets to have maxima and minima, and if not, that's supreme. So you do that what is needed to be done there. And here we take all linear combinations, because that's what's interesting to us. And for example, just to show that this pattern is not just available in these two places, and really what kind of closure we take, what kind of space we generate from a basic space, really depends on what we are interested in. Okay. For example, in another place, okay, which is very related with linear algebra, in fact, let's say if you're doing something like linear optimization. Okay. Just an example of how related these things are. Let's say if you're doing linear optimization. Okay. So let's say if you're doing something like, let's say you have a vector, or whatever, like 2x plus 3y, 3. Suppose say you want to maximize this. Okay. Let's say you want to maximize this. Then a lot of problems can be reduced like this. And let's say you have this condition x, y, z is greater than 0. And let's say you have some other condition. Okay. So, I mean, it could come in various forms. Like you could, you could just have a set of equation. Let's say x plus y plus z, you want it to be greater than 0, and x plus 2z plus 3y, you want it to be greater than 1. Let's say under these two conditions, or maybe less than 1, so that it becomes, under these two conditions, let's say, anyway, that doesn't matter. Under these conditions, let's say you want to maximize this function. Okay. Now in this kind of problem, the sets that you will be considering will be convex. Okay, so what
Would
I mean by
actually
that,
be less than one to make sense. Otherwise, it would be infinity.
otherwise it would be infinite. Yeah. So something like that, right? So,
Mhm.
or you have to just put some minus sign or something, right? So
Mhm.
yeah. So in these kind of questions, of course, this is a hyperplane, this is a hyperplane, right? So if you look at the set that you get in after doing it, it will be, like, it will be like a set which is cut out, which is the intersection of several planes. Okay. So I mean, like this plane, and probably we'll have some other plane. I don't know, like, so plane and the space on the part of the plane on one side, right? That's like this kind of thing is, right? It's like one side of the plane. It's the hyperspace, one side of a plane, either left side or right side. Okay. So like this one is, the positive side of x-axis, something like that. So it will be like a cutout of plane. So the region that you get is called a convex region. Okay. So in this kind of theory, whenever we consider, let's say, one solution, or let's say two solutions which satisfy these inequalities, then we will see that all certain kind of other combinations, like something called convex combinations, will also work. So there we don't need, their linear combinations will not do the work. Okay. There we'll need to take something called convex combinations. Because the our sets which are closed under convex combinations would be good contenders. Okay. And then we take the endpoints of those convex sets and their maximum minimum. There we take this. So it really depends on what we are doing. Okay. In vector spaces, we take linear combinations. They are easy. And
So,
yeah.
one doubt in this convex
Mm-hmm.
thing.
Hmm.
So, in 2D case, what we usually do is to plot the graph and take the endpoints, right?
Hmm. You take the
And
endpoints.
that are the candidates for maxima,
Yeah.
right?
Yeah.
But in 3D case, the intersection would be a line that would have infinitely many points.
No, but then there will be intersection of intersections, and they will be points.
Intersect, yeah, but
uh,
that could also be a line, right?
But no, but if you're in
Oh.
three dimensions, then intersection
Mhm.
of intersection would mostly
Yeah,
be a
yeah,
point,
yeah.
and those
Yeah.
tips will be the contenders for maxima and minima. Okay.
Mhm.
I mean, why that can be shown, like in a convex function, maxima always happens at the end point. I mean, we can discuss
Mhm.
that in analysis later on, but you
Yeah.
understand, right? Yeah. So the point is
Yeah.
that in different places you have to do different things. That is just not
Mhm.
a rigid thing. Okay. So yes. So now today, what we are trying to ask. So we have defined subspaces. We have seen that when you start with vectors, you take the subspace generated by that, or you take certain problem and its solution turns out to be a subspace. We have related these things. Okay. Now the problem that we are trying to tackle, okay, given a subspace or a space, whatever, given a subspace, find its generating set. Okay. And more importantly, more importantly, we will try to find its smallest generating set. Okay. Smallest generating set, and we'll see that they behave rather well. Okay, we will try to see that. Okay, but before getting into it, let's take a few examples of, so that we get geared towards understanding how smallest generating sets are defined, how smallest generating sets are usually found by without any theory or without any technique. So let's say if I take this collection of let's call it S3. Okay, so S3 is already a reserve, and let's call it S. Okay, this is the set of all real, okay, all real polynomials of degree at most 3. Okay, very well understood set. We all understand this is a vector space. So can people just give me a generating set for this? A subset that generates it?
What about x cube, x square, x and 1?
Okay, so we have x cube, x square, x, and 1. Hmm. So I hope it's clear to everyone that this indeed generates S. So when I write this
But
symbol, yeah.
this might not be the smallest.
So we'll see that. Yeah, we'll see if it is or not. Okay. So this definitely generates S. So in this context, it is clear that by this I mean you're only going to take linear combination. You're not going to multiply, because see, if you are allowed to multiply things, then the only 1 and x would have been enough. Right. You could get x square by multiplying, but of course there's no question that we are not there's no question that we are not doing that. Okay. Okay, so now the question is this the smallest or not? Okay, so yeah, so let's try to tackle this problem in general. Okay, let's try to tackle this problem in okay, someone is joining. Okay, she thinks she has left. Yeah, so okay, can anybody try to argue why this is the smallest? Maybe let's do it for this particular example, and then we'll try to
Because
tackle it
of
in
the
general.
degrees.
Because of the
Because of the
degree,
degree.
yeah, right, it's quite clear that you will need x cube, right? And
Yeah.
like if you have the x
You
square
can't generate x square from other lower degrees or higher
yeah,
degrees.
yeah, exactly. So you will need these four vectors, so it is the smallest, right? It is the smallest, right? So that was just a very simple example. Okay, so let's try to now do it in general. Okay, so let's say that v is a vector space. Now let's try to do some general arguments and build towards results. Let's say V is a vector space with V1, V2, V3 till Vk, okay, as a, of course, vector space over something. For the time being, we can just take over R, but in fact, it will work over any field, any place where you can, yeah, do the arithmetics. So with v1 v2 to vk as a generating set, as a generating set. At this point we're just taking finite, but soon I'll move into infinite also, where these are the generating set. Now, regardless of what vk is, this is a finite generating set, right? Meaning that every vector can be written as a linear combination. So let's see. So this means that any vector you take, any vector, maybe w, can be written as some linear combination, right? x1 v1, x2 v2, x3 v3, okay, dot 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 xk vk. Just saying that, it makes sense. Now you see, these VIs need to be actual vectors. We all understand that this vector space thing is general. It could mean polynomials. This each vi could be polynomial, it could be function, it could be anything that can be added. But we can just imagine we are working with vectors, and in fact we later on show that after we give coordinates, that it just, these are just behave like exactly like vectors. They are exactly vectors. After all, that's the abstraction we use to define these things. Now, whenever this thing happens, then we say that this, because usually what is the finite dimensional vector space is not is the definition. So this is the definition of it, okay? So such a vector space is called finite dimensional. So even without knowing anything about dimensions, if at all it has a finite generating set, that is the definition of finite dimensional, okay? Such a vector space is called finite dimensional, okay? Of course, finite dimensional over the base field R, okay? So that is the thing. Now our goal is to find the smallest generating set, okay? Yeah, so let's see. Okay, so let's first do this, keep this in the hypothesis, okay? Say that this v1 v2 till vk is the smallest, okay, is the smallest. So this is like the most optimal way to generate all the vectors. Okay, so every vector can be generated from this, and this is the smallest such set, okay, smallest size. So now, as expected, every vector will be generated in a unique manner, okay, right? For example, if we are in R2 and you take two vectors which are in different directions. Let's take you take this vector and you take this vector, okay? Then you take any other vector, okay? We know that using these two you can generate, and we know that 2 is the smallest in this case, okay? Now you take this third vector. How many ways do you think you can generate the third vector using v1 and v2? Yeah, only one way, right?
Yeah,
Because,
you
yeah, right, because from this w, this is the portion of the vector v2 that you are going to use. Wait, am I making sense or I'm just saying something wrong? Yeah, does that make so? Basically, what I'm saying is that if you're going to generate this vector v, then this vector v is going to be the sum of this vector and this vector, where this will form a parallelogram, right? So it will be sum of these two vectors. Now this point is unique, right? And this point is also unique. That's quite clear because it has to form a parallelogram, right? Yeah, and when you say that, then what do you get? Then you get that this portion is the multiple of v1 that you are going to use, the unique multiple of v1, and this portion is that unique multiple of v2 that you're going to use to get your w. You can of course prove this thing algebraically also, okay? This is just a visual way to see. this is the thing. So, I mean, since you're using the smallest size, you cannot afford to lose. You cannot afford to, have two, three different linear combinations giving the same vector. Then that's not the optimal, anyways. So that's one way to see it. The geometry is another way to see it. So that's how we expect. But in general, can we prove that every vector can be uniquely represented? So that's a claim then. Okay, claim every vector will be uniquely generated. So let's prove this on the other side. Okay, I'll just end the meeting and launch it again. It's already in the 1 minute end, so I don't